Cyber lesson day. All right, we're going to see how this works. But anyway, you have in front of you at this point a sheet of stoichiometry notes and a stoichiometry multimole problems. So what we're going to do is we're going to go through what stoichiometry is, and then we're going to go through how to solve these problems. Okay. So first, stoichiometry is just a chemical recipe. It's knowing how much of this I need compared to how much of that I need. The one I know best is the stoichiometry of internal combustion engines, because working on internal combustion engines for so long, and you need 11 moles of air, or 11 point something moles of air for every 1 mole of gasoline. So that's the perfect burning recipe for the engine in your car to run. But there's ways to calculate this, and the way in the notes they talk about this, they give you a problem CH4 plus 2O2. So carbon CH4 plus 2O2. So first I have to represent the CH4s. I have I don't have two CH4s. I have a CH4. I have two O2s. These are oxygens, carbons, hydrogens. And we're going to create CO2 and two H2Os. So CO2 plus 2 H2Os. So we're going to have a rearrangement here where we're going to have that one carbon attached to two oxygens, and we're going to have two oxygens that are connected to two hydrogens each. Plus this. And if we do the math, we can see that we have 4 hydrogens, 4 hydrogens. We have one carbon. We have one carbon on that side. We have 2 oxygens. We have 2 oxygens here and 2 oxygens. We have 2 oxygens here. So that's stoichiometry. Basically, I'm saying that for every 1 mole of CH4, I need 2 moles of O2 to create 1 mole of CO2 and 2 moles of H2O. That's what stoichiometry is. It's basically just figuring out what the recipe is. So you can do this with anything. Stoichiometry is not something that is just limited to chemistry. If I have 4 cars, right, without wheels, the last part of the assembly line, right? Yep, these are rough cars, but whatever. So I have 4 cars and they're the last stage of the assembly line. How many tires do I need? Well, if I have 4 cars, I need to figure out how many tires to get 4 cars complete. Cars TI, and I got to figure out what the subscript is here. We know that there's 4 tires on each car. So how many tires do I need? This is the big one here. It's kind of obvious. 4 times 4 is 16. I need 16 tires here to make 4 cars, 1 car, 4 tires per car. It's just a recipe. That's all it is. But in chemistry, it's just a little more odd to think about it that way. Okay, and so they give you an analogy of a sandwich, right? And they tell you that it takes 2 pieces of bread, 4 tomatoes, 2 pieces of chicken, and 1 piece of lettuce. So your equation there is I need 2 pieces of bread. We're just going to try and make it kind of plus 4 tomatoes, plus 2 slices of cheese, plus 1 thing of lettuce makes 1 sandwich, which is this complete thing. Oh wait a minute, they didn't capitalize that. Let's do that. TO4CH2LE. To make 1 sandwich. Sorry, I couldn't fit it all over there. But anyway, to make 1 sandwich, they give you this recipe. And then they ask you, what if I wanted to make 5 sandwiches? So all you're doing is you're just upping this to 5, right? And in order to make 5 sandwiches, in order to make this all true, basically I just have to multiply all the coefficients by 5, right? So I would need 10 BR plus 20 tomatoes plus 10 cheeses. Well, now I'm going to run out of room. Let's do it down here. 10 BR plus 20 tomatoes plus 10 cheese slices plus 5 lettuces to make the arrow to make 5 sandwiches. There's an easier way to do this. There's a way to actually calculate. It uses dimensional analysis because we're just converting moles to moles of something. It's very simple. So I'm not going to overload you, but let's talk about what they did here. So they use sandwiches again. So I'm going to write the recipe up here. 2 bread plus 4 tomatoes plus 2 cheeses plus 1 lettuce goes to make 1 sandwich, which is 1 BR 2 TO4 CH2 LE. So that's the equation they've given us. And then they're asking us to calculate. All I did was calculate 5 times that, but there's a dimensional analysis way. So if I need 5 BR2TO, I keep wanting to write that O, TO4CH2LE. If I need 5 of these, and I know that 1 BR2TO4, I keep wanting to write that O big, O4 because it's not a chemical, CH2LE, and oxygen is. For every 1, I need how many what? So here they have you figuring out tomato, chicken slices, lettuce. Let's just do tomatoes. I need 4 tomatoes, right? 4 coefficient right there to make 1 coefficient right there to make 5. So I know that 5 times 4 is 20 tomatoes, 20 tomato slices. And that's how we're going to use dimensional analysis. I'm not a big fan of writing it, doing sandwiches this way because obviously it doesn't leave you, it leaves you confused. So what I'd like to do is look at the chemicals. So they show it pictorially. They show H2 plus O2 goes to H2O. But it's not balanced, so we got to do 2 of these and 2 of those to balance it. So we're going to have this many and 2 more H's, or 1 more H2 up here. Now it's balanced. 4 hydrogens, 4 hydrogens, 2 oxygens, 2 oxygens. So now we know what the ratios of moles to each other. And this refers to how many moles or molecules interchangeably. As far as stoichiometry is concerned, I call them moles because when we put them in the equation, we do it as moles. And so they're asking you a question there. They're saying, so how many moles of oxygen are needed to react with 6 moles of hydrogen? Okay, so we're going to set this up like a dimensional analysis. And what's given? What's given is 6 moles of hydrogen, right? 6 moles of hydrogen, H2. Now you're going to figure out why we wanted those units very specifically on there. And so, what units have to be down here? Moles of H2. Now we have a bad habit we have to ditch because we're so used to writing 1 mole every time. Now we're converting moles. You will write 1 mole when it's under grams or under molecules or under atoms or anything like that. But here we don't do that anymore. Now we're doing mole conversions. So what are we converting to? We want to convert to moles of oxygen. Moles of O2. That's the units of my answer. Moles of O2. Now, here's the part that people get hung up on. Where do these two numbers come? Well, they come directly from your balanced equation. You said that for every 1 mole of oxygen, we know there's a 1 out in front because we don't like to write 1s, but we know it's there, right? Just like that 1 that's beside oxygen here. How many moles of H2? Well, if I look up here, 2 moles of H2. 2 moles of H2. And now it's a division problem. 6 divided by 2 is 3 moles of oxygen. I need 3 moles of oxygen. And I can actually do that. Like I could draw 6 molecules up here and it would take me 3 molecules of oxygen. We can see the ratio is 1 to 2, 1 to 2, right? So it's pretty easy to kind of simplistically understand that this is basically a ratio. And you can do different problems with the same balanced equation because I'm going to do a few examples here. Let's see what we're converting from and to. All right, but the rules still apply. The rules to dimensional analysis, it's not like they just disappear. You absolutely have to go by the rules of dimensional analysis. So whatever units here are the units here, whatever the units of my answer, go both places. All right. How many moles of water are produced if you react 2.5 moles of oxygen? So what I'm given is 2.5 moles of oxygen. Units, moles of oxygen. And they want to know how many moles of water are produced. Moles of H2O. Units of my answer, moles of H2O. You'll love the fact that there's no more writing molecules and all that stuff. Basically, from here on in, it's moles and grams for stoichiometry. All right, how many moles of H2O? 2 moles of H2O. For how many moles of oxygen? For every 1 mole of oxygen. Now, instead of a division, it's a multiplication. 2 times 2.5 is 5 moles of water. 5 moles of water. If I had 2.5 moles of O2, I can make 5 moles of water, right? That's why I think it's more helpful to think about these in terms of moles instead of molecules, because you can't have 2.5 molecules, but you can definitely have 2.5 moles of O2. That would be 32 grams, plus that'd be 64 grams, plus 16 would be 70 something grams of oxygen. Anyway. So that's how we solve these problems. Let's do this last one here. Actually, I'm going to do a couple of examples using a very similar equation to this. Let's do that. Okay. Let's see. If 0.5 moles of water are produced, 0.5 moles of H2O. Don't get hung up on the words. My big advice to you is don't get hung up on what the words say. You're going to be given something and they're going to be asking you something. That's how I always solve these. It's never failed me yet. So this is moles H2O. And if 5 moles of water are produced, how many moles of hydrogen reacted? How many moles of oxygen reacted? So they're actually asking that both ways, but we're just going to do the top one there where we're doing moles of hydrogen, moles H2. And so now again, what are our coefficients? Moles H2, moles water. 2 over 2 is 1. 0.5 times 1 is 0.5. Moles of H2. Moles of H2. Okay, now what I want you to do is grab your sheet that says Stoichiometry mole to mole problems. And the first thing you're going to have to do is you're going to have to balance something. So you're going to balance an equation. I'm going to do this one first for you. Okay, so under the examples that I'm doing, I have an equation. I have N2 plus H2 goes to NH3. And let's balance this up. So I have 3, so I'm going to have to do 2 here, 3 here, 2 nitrogens, 6 hydrogens, 2 nitrogens, 6 hydrogens. So I'm balanced now. And the first question asks me, example question, if I have 5.6 moles of hydrogen, how many NH3 can I make? So it's a dimensional analysis. I have what? 5.6 moles of H2, 5.6 moles H2, moles H2, and they want to know how many moles of NH3 I can make. NH3, moles, NH3. And there's always going to be a mole conversion in every problem. Every problem we do during stoichiometry, there's always going to be what we call the heart of the problem. And that's where you're going to have moles of the one thing over moles of the other. If you don't have that, or if you have it more than once, or if you don't have it at all, you'll know that something bad has happened. But we'll go into that when we start doing grams, moles, grams, grams. Right now, all you have is the heart of the problem, which is a mole ratio. And I know that for every 2 moles of NH3 I make, I'm using 3 moles of H2. And now it's a math problem. And now you actually, when I say multiply across the top and divide by the bottom, now you actually have to start doing that. So I have 5.6 times 2, enter, divided by 3, enter. 3.73 repeating. 3.733 repeating. Moles of NH3. That is the first example problem. These are pretty freaking easy, right? There's nothing too tricky to them. The only thing that's going to get you is the wording. If they ask for a product or something other, if they ask for a reactant, sometimes y'all get a little squirrely when they start asking for a reactant. It doesn't matter. The problem works no matter what you're searching for, as long as it's moles of one thing to moles of the other. So I have 2.4. It says if I manufacture 2.4 moles of NH3, how many moles of N2 did I use? Okay, again, it's a dimensional analysis. So what am I given? I'm given 2.4 moles of NH3. NH3, moles NH3. And what are they asking me? How many moles of N2 it required to make that? Moles N2. Moles N2. And so again, heart of the problem, All I'm doing is looking for that ratio. So moles N2, 1 mole of N2. Moles of NH3, 2 moles of NH3. 2.4 divided by 2 is 1.2 moles of N2. That's how simple these are. So what I want you to do for the next 20 minutes or so is I want you to try working on the rest of these stoichiometry mole-to-mole problems. It's just setting up a conversion. First of all, it's balancing. You got to be able to balance. At this point in your chemistry career, if you can't balance, somebody beside you, somebody in this room knows how to balance better than you. You should practice, because stoichiometry, you just did the last test. You saw none of it was multiple choice. This next test, none of it is multiple choice. So guess what they're going to make you do? They're going to make you use names. They're going to make you, nitrogen trihydride. Yeah, you're going to have to go from a name to a formula. You're going to have to balance. I told you these things never go away. Maybe you didn't believe me, but here's proof. And then you're going to have to write it out. You're going to have to write out everything just like this. This would be full points because I have all my units and I have all my numbers and they're all correct. Anyway, give it a crack. Somebody in this room has got to get this fairly well. And I will see you guys on Monday. Tomorrow, I'm going to refresh your memory on names and balancing. I just have to make sure that everybody knows how to get there. I'm probably going to post a video for that. You won't need it. You're just going to go to work. But if you do need it, there's going to be a video on my YouTube page. I'm going to put it on my e-class. I'm going to make sure that it's everywhere so there's no reason not to see these. All right, guys, I will see you on Monday. Good luck.